Section: Introduction. In this section, we discuss the advancements in large language models, LLMs, and how test time scaling, TTS, can enhance their reasoning abilities by using more computational resources during inference. We categorize TTS into two types: internal TTS, which trains models to think more slowly and methodically, and external TTS, which improves reasoning through sampling or search methods without changing the model itself. A major challenge with external TTS is determining the best way to allocate computational resources for different problems. Current TTS methods utilize process reward models, PRMs, to guide the generation of answers and optimize computation. However, there is a lack of thorough analysis on how policy models, PRMs, and the difficulty of problems affect TTS strategies. This gap limits our understanding of TTS effectiveness and the development of optimal strategies. To tackle these issues, we aim to explore how policy models, PRMs, and problem difficulty impact TTS through detailed experiments. We will also examine the characteristics and performance limits of TTS methods. Our experiments will involve various PRMs and policy models across different tasks, revealing that the best TTS strategy depends significantly on the specific model and problem difficulty. Notably, smaller models can outperform larger ones in challenging tasks when using optimal TTS strategies. Our contributions include a thorough evaluation of TTS methods with updated policy models and PRMs, emphasizing the importance of rewards in the TTS process. We introduce a reward-aware compute-optimal TTS approach, demonstrating that scaling strategies differ based on the models and problem complexities. Our findings indicate that smaller language models can surpass larger ones, with examples showing that a 3 billion parameter model can outperform a 405 billion parameter model in specific tasks. Next, we formulate the reasoning problem as a Markov decision process, MDP, which includes defining the state and action spaces, transition functions, and reward functions. We describe how the policy generates actions based on initial prompts and how the process continues until it reaches a conclusion. We also consider three TTS methods: best of n, BON, beam search, and diverse verifier tree search, DVTS. We do not evaluate methods that involve look-ahead operations, as they are inefficient. In the BON method, the policy generates multiple responses, and we use scoring and voting to determine the final answer. Section Summary. In this section, we discuss the advancements in test time scaling, TTS, for large language models, LLMs, highlighting its two main categories: internal TTS, which trains models to reason slowly, and external TTS, which optimizes computation allocation for problem solving. We emphasize the need for systematic analysis of factors like policy models and problem difficulty in TTS strategies, demonstrating through experiments that smaller models can outperform larger ones by employing compute-optimal TTS methods. Section: Beam Search. In this section, we describe our approach to beam search. Given a beam width and size, our policy model first generates a set number of steps. The verifier then picks the top steps for further exploration. We continue this process, sampling additional steps for each selected one, until we reach a maximum depth or generate an end-of-sequence token. To enhance diversity, we introduce diverse verifier tree search, DVTS, which builds on beam search by splitting the search into multiple independent subtrees. Our findings show that DVTS performs better than traditional beam search on easier and medium-level problems when we have a larger computational budget. We also observe that increasing the number of parallel subtrees is more effective than simply widening the beam under the same budget. Next, we discuss compute-optimal test time scaling, TTS. We propose a strategy that selects hyperparameters tailored to specific prompts to maximize performance. For a given prompt, we define a function that represents the output distribution produced by our policy model with certain parameters and a compute budget. We aim to find the optimal scaling strategy for each problem based on this function. We emphasize that our compute-optimal TTS should be aware of rewards. Previous approaches have used a single reward model, PRM, as a verifier. We differentiate between on-policy PRMs, which provide accurate rewards for the policy model's responses, and offline PRMs, which may struggle with out-of-distribution issues. Training a PRM for each policy model can be resource-intensive, so we explore a more general approach where the PRM may be trained on a different model. In our analysis, we find that rewards significantly impact the response selection and generation process. For instance, one PRM may favor shorter responses, leading to incorrect answers, while another produces correct answers but consumes more tokens. Our empirical studies confirm that rewards greatly influence TTS performance and output. Based on these insights, we propose integrating rewards into our compute optimal TTS strategy. We define a reward function and adjust our output distribution accordingly, ensuring that our strategy is adaptable to the policy model, prompt, and reward function. This leads to a more comprehensive framework for practical TTS applications. Section Summary. In this section, we describe our approach to enhancing beam search through diverse verifier tree search, DVTS, for improved performance and diversity, and we introduce a compute optimal test time scaling strategy that incorporates reward functions to optimize response generation based on specific prompts. Our findings indicate that integrating rewards significantly influences the generation process and outcomes, leading to a more effective and adaptable framework for test time strategies. Section. Absolute problem difficulty criterion is more effective than quantiles. In this section, we explore the effectiveness of the absolute problem difficulty criterion compared to quantiles. We categorize problems into 5 difficulty levels based on pass at 1 accuracy. However, we discover that using these levels based on quantiles is not effective, as different policy models have varying reasoning abilities. For instance, the model 0.5 to 72B instruct achieves over 80% pass at 1 accuracy on 76.2% of the 500 problems. Therefore, we opt for absolute thresholds to define difficulty levels: easy, between 50% and 100% accuracy; medium, between 10% and 50% accuracy; and hard, between 0% and 10% accuracy. Next, we aim to answer several questions. How does test time scoring, TTS, improve with different policy models and process reward models, PRMs? How does TTS vary for problems of different difficulty levels? And do PRMs show bias towards certain response lengths or sensitivity to voting methods? For our experiments, we utilize competition-level mathematical datasets, including a set of 500 representative problems. Given the advancements in large language models, LLMs, in mathematical reasoning, we also include more challenging problems. We employ policy models from the Llama 3 and 0.5 families, specifically using the Instruct versions. For PRMs, we evaluate several open-source models. The PRM7B is trained on a specific dataset, while the Skywork series includes models trained on different mathematical datasets. The 0.5 Math series features models that are particularly strong for mathematical tasks, with 0.5 Math PRM72B being the most capable. In terms of scoring and voting methods, we consider 3 scoring methods: PRM-min, PRM-last, and PRM-avg, along with 3 voting methods: majority vote, PRM-max, and PRM vote. We calculate scores for each trajectory based on these methods. For example, PRM-min scores by the lowest reward, PRM-last by the last step's reward, and PRM-avg by the average reward across all steps. The voting methods then determine the final answer based on these scores. We use an open-source LLM reasoning framework for our codebase and set compute budgets to specific values in most experiments. The division of steps follows established formats, and we set parameters for beam search and other methods accordingly. Section Summary. In this section, we establish that using absolute thresholds for problem difficulty, rather than quantiles, is more effective for evaluating test time strategies, TTS, across various policy models and problem difficulties. We also outline our experimental setup, including datasets, policy models, process reward models, scoring and voting methods, and compute budgets used in our analysis. Section: How does TTS improve with different policy models and PRMs? Q1. In this section, we explore how text-to-speech (TTS) improves with different policy models and prompt response models (PRMs). We find that PRMs are difficult to generalize across various policy models and tasks. For instance, with the LLM A3.1-8b instruct model, we see that search-based methods using Skywork and 0.5 math PRMs perform much better with larger compute budgets, while other PRMs do not show significant improvement and can even perform worse than majority voting. Similarly, for the 0.5-7b instruct model, Skywork PRM-7b and 0.5 math PRMs scale well with increased budgets, but other PRMs still perform poorly. Although the accuracy of both policy models improves with larger budgets, the overall improvement in TTS remains moderate. This indicates that generalizing PRMs across different policy models and tasks is particularly challenging, especially for complex tasks. The best TTS method often depends on the specific PRM used. For example, Bond generally outperforms other strategies when using certain PRMs, while search-based methods excel with Skywork and 0.5 math PRMs. This discrepancy arises because using a PRM for out-of-distribution (OOD) policy responses can lead to suboptimal results, as PRMs struggle to generalize across different models. We also notice that selecting each step with OOD PRMs can result in answers that are stuck in local optima, negatively affecting performance. This issue may be linked to the base model of the PRM, as those trained with 0.5 math 7b instruct show better generalization than others. Our findings suggest that the choice of the optimal TTS strategy is crucial and should consider the specific PRMs used. Next, we examine the relationship between TTS performance and the process supervision abilities of different PRMs. We find a positive correlation, where TTS performance increases with better process supervision abilities. The fitted function indicates that TTS performance is related to these abilities in a logarithmic manner. We also investigate how the optimal TTS methods vary with different policy models by experimenting with various sizes of the 0.5 family of large language models, LLMs. Our results show that for smaller models, search-based methods are more effective, while larger models benefit more from Bond due to their stronger reasoning capabilities. In addressing how TTS improves for problems of varying difficulty levels, we categorize tasks into easy, medium, and hard based on pass-at-1 accuracy. We find that the optimal TTS methods differ across these categories. For smaller models, Bond is better for easy tasks, while beam search is more effective for harder ones. For models with parameters between 7b and 32b, DVTS works well for easy and medium tasks, and beam search is preferred for hard tasks. Interestingly, for the largest models with 72b parameters, Bond performs best across all difficulty levels. Lastly, we observe that PRMs tend to be biased towards the length of the steps. Even with the same budget, the number of inference tokens varies significantly between different PRMs. For example, the scaling with PRM-DEEP-SEEK-8B consistently produces nearly double the number of tokens compared to PRM-8B. This bias may stem from the training data, which we analyze and find that the training data for DeepSeek PRM data is longer than that for PRM data. This suggests that the length of the output can be influenced by the training data characteristics. We also note that while the number of inference tokens for 0.5 math 7b is larger than for Skywork PRM-7b, their performance is quite similar, indicating that searching with Skywork PRM-7b is more efficient. Section Summary. In this section, we analyze how TTS performance varies with different policy models and PRMs, finding that the optimal TTS method depends on the specific PRM used and the size of the policy model, with larger models favoring Bond and smaller models benefiting from search-based methods. We also categorize task difficulty levels and observe that TTS strategies should be adjusted accordingly, as biases in PRMs can affect output length and efficiency. Section: PRMs are sensitive to voting methods. In this section, we examine how PRMs respond to different voting methods. Our results indicate that Skywork PRM7B performs better with PRM vote compared to PRM Max, while 0.5 Math PRM7B shows little sensitivity to these methods. This difference arises because the training data for 0.5 Math PRMs is processed to eliminate incorrect intermediate steps, which enhances the accuracy of the output rewards. This highlights the importance of training data and improving error detection during the search process. Next, we explore the Compute Optimal Test Time Scaling (TTS) strategy. We pose several questions. Can smaller policy models outperform larger ones using Compute Optimal TTS? How does Compute Optimal TTS compare to majority voting? Is TTS more effective than long-based methods? Regarding the first question, we find that scaling the test time compute of smaller policy models is vital for enhancing the reasoning performance of large language models, LLMs. We compare LLAMA 3.2 to 3B instruct using Compute Optimal TTS with Llama-3.1-405B instruct on 2 tasks. Our findings reveal that LLAMA 3.2 to 3B instruct outperforms LLAMA 3.1 to 405B instruct, demonstrating that smaller models can indeed surpass much larger ones when using Compute Optimal TTS. We also observe that increasing the compute budget allows LLAMA 3.2 to 1B instruct to outperform LLAMA 3.1 to 405B instruct on one task, although it underperforms on another. Additionally, we see that small models like 0.5 to 0.5B instruct can exceed GPT-level performance with Compute Optimal TTS. In our FLOPS comparison, we assess whether Compute Optimal TTS is more effective than simply increasing model size. Our results show that smaller policy models can outperform larger ones while requiring significantly less inference flops, reducing total flops by a factor of 100 to 1000. Finally, we summarize how Compute Optimal TTS improves upon chain of thought, COT, and majority voting. We find that Compute Optimal TTS can be 256 times more efficient than majority voting and enhances reasoning performance by over 154%. However, as the number of parameters in the policy model increases, the benefits of TTS diminish, indicating that its effectiveness is closely tied to the reasoning ability of the model. For models with weaker reasoning skills, scaling test time compute leads to significant improvements, while for stronger models, the gains are more limited. Section Summary. In this section, we demonstrate that smaller policy models can outperform larger ones using the Compute Optimal Test Time Scaling (TTS) strategy, achieving significant improvements in reasoning performance while requiring less computational power. Additionally, we find that Compute Optimal TTS is substantially more efficient than majority voting, enhancing reasoning capabilities by over 154% for models with weaker reasoning abilities. Section: Is TTS more effective than long COT-based methods? Q6. In this section, we examine whether TTS is more effective than long COT-based methods. Recently, long-based methods have made significant strides in mathematical reasoning, and we compare TTS's performance against these methods. For our evaluation, we consider several approaches. 1. A method that generates reasoning data using Monte Carlo tree search, MCTS, and then learns online policies and preferences. 2. EURUS2, which boosts reasoning abilities of large language models, LLMs, through implicit rewards and online reinforcement learning, RL. 3. A method that mimics self-reflection with limited training data. 4. A method that learns the format first and then enhances reasoning through RL. And 5. Distill-Quen 7B, which distills a large number of high-quality reasoning samples from a massive model into a smaller one. Our results indicate that TTS with a specific model outperforms the other methods on simpler tasks, but while its performance is close to Distill Quen 7b on one task, it drops significantly on another. This suggests that TTS is more effective than methods using direct RL or supervised fine-tuning on MCTS-generated data, but less effective than distilling from strong reasoning models. We also find that TTS performs better on simpler tasks compared to more complex ones. We also discuss the scaling of LLM test time compute as a way to enhance performance. Previous research has looked into various methods like majority voting and search-based techniques. Some approaches focus on verification-guided compute, while others propose self-evaluation methods to improve efficiency without needing external rewards. Our goal is to provide a systematic evaluation using updated policies and verifiers on more challenging tasks, along with principles for practical TTS. When it comes to improving mathematical reasoning abilities, we categorize methods into training time and test time strategies. Training time methods include large-scale pre-training and supervised fine-tuning, while self-training strategies enhance reasoning through fine-tuning on self-generated solutions. Test time methods, such as prompt-based approaches, help models break down problems into smaller steps, improving accuracy. Techniques like self-refinement and external tool integration further enhance reasoning capabilities. Our work focuses on improving reasoning performance through scaling test time compute using PRM-guided search methods. Lastly, we note that process reward models, PRMs, have proven to be more effective than outcome reward models, ORMs. However, gathering high-quality PRM data can be expensive. We explore automatic data collection methods and advanced PRMs that utilize various modeling perspectives. With the rapid development of PRMs, we aim to provide a comprehensive evaluation and guidelines for their practical development, releasing the most capable PRMs for mathematical tasks available today.